class to work on that problem set with my help. All right, how about you?
The antiderivative was
No, it should be negative minus. Oh, wait, negative.
I thought too, because you said
No,
like.
No.
You could, didn't I remember your that is? You have to integrate first, though, so you can it's the one half of your power rule.
that's negative.
Yeah.
Yeah.
I don't know if you.
We have negative exponents for answer.
What?
Negative exponents.
All right, would you like some more time to work, or should we start to talk about them?
Like 2 minutes.
Like 2 minutes? Sounds good. Again, these are all problems I would feel very comfortable putting on your test next time.
I got the
How do
negative.
we, you said this was negative.
No, because it's negative.
You know, these are derivatives, you're doing anti-derivatives, so you're kind of going backwards here. So you're taking what was sine and you're going back to it. So then the negative sine, what the.
Right. But derivative of 3 cosine X is negative 3 sine.
What's that?
Yeah.
No, it's not. It's negative, negative. So,
Okay.
1 minus, negative 1 minus 3 is negative 4. That's mine. Yeah, no, minus 3.
And then down. Oh, okay, I get it. So
Alright, so we have to simplify this one first. What tracing do you know that's equal to tangent? There's 2 fractions, 2 functions I put in a function.
They think are
You use sine over cosine to simplify, and then you get integrated. It's gonna take 2 steps.
So how do we plug in the derivative
Math
of
9.
the derivative of tan?
Secant squared,
Secant squared.
that's a derivative.
So if there's already, if you want to put like if you want to put like
you're gonna have to simplify that before you get going, so you're gonna need to pre-cal knowledge what the tangent equals to help you simplify before you integrate. Interesting, because this was just like. All right, let's talk these through. So, number one should be something that if I put this on the test, literally everyone should get it right, because this is just straight up power rule. All right, let's see if that's right. So we're doing new power would be x cubed on this one. We're adding 1 to the power, and we divide by that new power. So you could do 9/3, or 3 does work. Here, new power would be squared. 4 divided by 2 is 2. I like adding the x to the 3 and then plus c for all of the constants. All right, number 2. Can I just integrate the top and the bottom and just call it a day? The answer to the first question is no. I have to simplify this first. I don't have a product rule. I don't have a quotient rule, so I got to simplify this. You can divide each of these things by x squared, or a lot of students like to bring that up to the numerator. If I bring that guy up to the numerator, what power would be on him? -2. And then I would need to distribute. I don't have, again, a product rule, so I have to make sure it's just number times x to some power, number times x to some power. All right, x squared times x to the -2, or you can think of that as x squared divided by x squared is just 1. And then that would be plus 5x, and then plus 6x to the -2. Notice with my notation, my integral symbol and my dx are staying because I haven't actually integrated yet. Now when I integrate, 1 will integrate into what? X. What about 5x? Okay. And then what's the new power on this last term going to be? -1. So I'm going to change this into -6. Anything missing? Cool. All right, we had a similar one in the problem set where you had to multiply out before you took an integral. Just make sure you can't do anything where there's a division or multiplication. You got to simplify that first. So speaking of multiplication, does anyone recognize this as one of my trig derivatives? You do? What's that the derivative of? Tangent times cosine? That's not one that I know. Yeah, so what's up? I don't know. Let's find out. So we're going to use some pre-cal knowledge right here of what tangent is equivalent to. Tangent is a fraction of 2 functions. Anyone know those 2 functions? Sine over cosine. Anything convenient happen when I plug that in? The cosines will cancel out. We have 1 in the denominator, 1 in the numerator. Now you could simplify this, or you could leave it as 2 separate terms. We've got sine x minus 3 sine x. So I'm going to go ahead and make that -2 cosine x. The -1 minus 3. So I have 1 of them and then -3 sines. All right. The -2 is going to hang out. What is the integral of cosine? Let's go with regular sine and plus c. Oh, shoot. I'm an idiot. I did too many things at once. All right, let's try that again. So -2 sine x dx, so then +2 cosine x plus c. Perfect. Much better. All right, our last one, an integral with bounds. We won't do much of this today with our U-substitution because U-sub with bounds is a little bit weird. What might be useful to rewrite in this integral before we get started? The square root, what power is that? Perfect. All right, so I'm going to raise this to a new power. I'm going to go 3/2. What number would I put out front? 2/3. I can multiply by that reciprocal instead. What about this fraction? Ugh. I'm gonna go x squared, and then I'm gonna divide by 2. What was the notation for, hey, I integrated, but hey, I did not plug in my bounds yet? Our vertical line and throw those bounds on it. Now I'm gonna plug in my bounds. Which one goes in first? 4. Are you sure? Yeah, I would check to make sure, just because sometimes it won't. But in this case, since I have just x the powers, it will turn into 0. All right, let's say this were a multiple choice question and I wanted to simplify it. Anyone know how to do 4 to the 3 halves? Why is it 8? All right, I could do 4 cubed and square root it. That's 64, then square root. Or I can square root, then cube it. That's what I would do because I like making numbers smaller first. So square root of 4 is 2, then I cube it. So I've got 2/3 times 8 is 16/3. Let's see, 4 squared is 16, divided by 2 is 8 times 3. What is that, 24? I think so. Oh, 24 in thirds. All right. 60, 72. And then we should get 88 over 3. All right. I told Herbie, because he was asking if this question was right, and I told him that he could check it on his own in the calculator. Let's remind ourselves how to do that on the calculator, just because next class there will be some questions on the test that do require you to use your calculator. Think of like the rate in, rate out questions. So here, anyone remember where I went to get an integral? Math 9. All right, I can type this in 0 to 4 square root x. What was it, plus 3? Oop, not like that.
X root x plus 3x.
Plus 3x. Sick. And enter. All right, looks like it's rounding towards the end, so I'm just going to type in 88/3 to compare instead of doing math rack, and I get the same number.
I just multiplied that by 3.
Yeah, you could do that too.
Are we gonna go through anything?
You'll get it for part of the test. Part of the test is non-calculator, because on a question like this, I wouldn't want you to be able to just do it on the calculator. Part of the test, though, will require the calculator for some of the more complicated questions. So stuff like we did in applications of integrals, where we did stuff like this, definitely you'll have a calculator. All right. So if that felt uncomfortable, you got resources. There is a full-on test review with a, oh, my answer key's not posted yet. I'll make sure that's posted by the end of today. But very similar questions you can see on our first page here. Numbers 1, 2, and 3 look remarkably similar to some of the questions we just did. So I would make sure that you are comfy before we hit round 1 next time. Yeah, absolutely.
It's almost like it was inspired.
What?
They were inspired by each other.
Yeah, it's almost like I'm not a very creative lady. For those of you that were absent last time, I can pass around test reviews now. Do I have them in here? Where did I hid them from myself somewhere. I was remarking last class about how much I liked that test review. The test review that I'm going to give you in a second was the test last year. So it is a test that I liked very much. So probably a test that is going to look similar to the test I give you next time. All right, anyone else? Who else needs a test for? All right. So again, this was the test last year. So I'm writing a new test this year, obviously, but yeah, absolutely. All right, are you guys ready to start our second to last unit of the entire year? Isn't it? Crazy talk. All right, this is one of my favorite lessons, and we're only going to do maximum 10 problems today together. Are ready for a bad joke? Are you excited?
Oh, I get it. I get it. I was waiting for it.
I guess we can do a number talk. I did some review questions for our test instead. All right, let's look. What day should we do? Should we scroll to the end and see what's in here? Oh, this one makes people angry. We'll do this one. All right, there's a video reveal. How many packets of ketchup will fill the container?
I know this because I feel the container similar.
Yeah, I'm gonna say 6.
I'm gonna go 5.
Do I need to record the guesses or are we
I
just
did
verbally saying?
I did in the bathroom. I also put ketchup packets on
Yeah,
the
like 6 is fine.
I think when you sat down and
All right, anyone want to claim a number that's different than 6 or 5? 4.
I'll go 3.
Yeah, we gotta figure it out.
One of that.
All right, who said 6?
I did.
Kirby. All right, who says 5? Evan. I heard 4 as well. Anyone want to claim 4? All right, Walt, Mallory. Johnny 2. Anyone else?
3.
3 says Chris and Derek. All right, anyone want to claim different? Anyone else?
Man. Oh, just trying to take it.
All right, anyone else?
I just want everyone to keep in mind that this has human error in it.
It
You
does.
never get all of the ketchup out the packet.
Fair. All right, here's your video reveal then.
Or is it like sped up, or you have to watch them slowly push
I think
out
it's
all
sped
of the
up.
ketchup?
It's 40 seconds long, so it might not be sped up. It's not really sped up at all. Slightly. He's doing a really good job of trying to squeeze all the ketchup out, though. Looks like Jello.
That's full.
Oh, that's over.
That's full. That's over.
No, he's kidding.
No, he's
He's
not.
over the lip.
He's like filling it.
What is he
It was
doing?
more. It was
What
more.
is
It
this?
was more.
What is this?
Trying to see how many you can put on there.
Yeah!
I was right.
Let's go.
Let's go. You know, it's over the lip.
No one in their right mind would fill it up.
Like 2 packets.
Wrong.
I don't make them. Don't tell me.
Overruled.
Let's go. Yeah,
No.
Hey, we won together.
All right, so now that you all are all good and angry,
No, you just have to win.
all right, so to be really clear, the stuff that we're doing today is not on the test next time, though you may be able to use it for some questions next time. Yeah, a little bit. We're going to talk about essentially undoing chain rule today. So you may have noticed that all of the integrals we've been taking so far are of functions where I can simplify them down to a power rule or ones that involve trig. So for example, the question we just did on the do now that we were doing, where it had that division problem, I was able to simplify it down to a number times x to a power, a number times x to a power, a number times x to a power. We don't really get the same types of rules that we do when we took derivatives. So when we took derivatives, we had a product rule that helped us when we were multiplying things. We're not going to have that for integrals this year. If you take BC next year, there is a method for that, but we're not going to learn it this year. So any product, we have to be able to simplify. Quotient rule, there just straight isn't a rule that reverses that for integration. So we won't ever get a rule for that, even if you do take BC next year. Now, chain rule is one where this opens up a lot of doors because right now, speaking of opening doors, I'm going to close this one. So thinking of things like sine x, I can integrate sine x, but as soon as I make that like sine of 2x, I now am lost. I have nothing to do. So as soon as I put functions inside other functions, I'm kind of lost. Like square root of x, I can do. Square root of x plus 1, I'm lost. What do I do? So that's what we're going to try to do today. We're going to try to undo if we have our chain rule. What the heck does this say at the top? All right, there's a big old typo here. Did I copy the wrong notes onto here? Hold, please. You tell me what's wrong. Look at that chain rule.
That doesn't look like a chain.
It's, yeah, because it's wrong. Check. What are the, oh, I'm sure we can do that. Matthew. Why are you being sassy today? All right. I don't like all this sass. All right. So it's wrong on your paper too, so let's fix it. Darn, I must have copied the wrong one. So let's fix it. Chain rule. Do I have plus C's in chain rule? No, because that's a derivative. I meant to multiply here by something. What do we multiply for chain rule? Anyone remember? Yeah, derivative of g of x. So let's make this g prime of x. All right, so apologies on that. I must have copied and pasted something weird. So we've got the idea that we want to reverse chain rule. So you're going to notice this guy here is the same thing as this integrand here. Now, what? Which one? This guy? We'll get there in a second. All right, so what we're going to try to do is reverse this process. So notice I took a derivative here to get this. We're trying to go back and take an antiderivative to get here. What you're going to notice is these integrals look relatively complicated. So what we're going to try to do is use the letter u and make a substitution to make this integral look less complicated and easier to do. Some questions you may have. Why the letter u? I don't know. Textbooks use that one. You can use any letter that you want that doesn't have a meaning already. So if Matt wants to do M sub, if Sadie wants to do S sub, Evan is not allowed to do E sub unless he uses a capital E because lowercase e already has a meaning. So we're going to go from easiest to kind of hardest. So I'll kind of walk you through the process. This set of notes is one that kind of lends itself well to color coding. So if you like to color code your notes, today may be a good day to grab out 2 colors of highlighter or like 2 different colored pens. If you don't care, I'll color code my notes so you can kind of see them. So the idea that we're going to do is we're going to use 2 things to substitute. I'm going to find out what I think u should be, and we're going to spend a lot of today talking about how to choose what u is. Just like for chain rule, u is going to be whatever would be inside the other function. So if you felt like you should chain rule something, that thing that you would chain rule is going to be your u. We are then going to find du, which is the derivative of u. We're going to do that kind of outside of what we're doing in the rest of the problem, but we're going to substitute for that as well. After we substitute, we're going to be able to integrate and we'll get f of u plus c. One year I was mad at my student while I was teaching this. So I said, and you'll get fu plus c. And everyone laughed and he didn't get it. And it was funny. All right. But I had a big F that year. So it was like, and a big fu plus c. No.
Because it was just math.
Yeah, it's just math. I did on video. It was. All right. So let's go through a couple of problems. Really, this gets a lot better the more you practice with this. So I'm going to roll you through. It does help with being pretty organized for these problems. So the way I'm doing this problem and the way I'm organizing my work is super important. So I'm going to model for you what I think the best process is. So first of all, we have to figure out when we're supposed to use this method at all. So looking at this first integral right here, I'll make it real big. Do you guys see a function inside another function?
Yeah.
Yes. All right. What is that inside function? All right. I see x squared plus 1. It is inside the function squared. So I'm going to set u equal to x squared plus 1. All right. So we're looking for, like, if we were to take a derivative, the thing we would chain rule. It's supposed to be inside another function. All right, now I'm going to kind of ignore the top question for a second and find du, the derivative of u. And I literally say it like that every time just to be a little bit repetitive. All right, it is 2x, but I'm going to do something a little bit weird with the derivative. Normally, we would write like du dx to say the derivative of u with respect to x. I'm going to take this derivative, what I would call kind of differential style. So instead of putting the dx on the bottom, I'm actually going to keep the dx over here. So kind of thinking of it like I multiplied over the dx. I'm using pretty strong air quotes because it's not really a fraction. Or you can think of it kind of like related rates or implicit where we have like a dx dt after everything. Just we're going to keep that dx on the right-hand side. All right, so now let's peek back at our original problem. Do you guys see 2x dx anywhere in our problem?
Yeah.
Yeah, he's chilling at the end. So 2x dx is a, goodness gracious, we're scrolling all around, is equivalent to du. U is equivalent to our x squared plus 1. Now, notice what I'm highlighting. I've highlighted literally everything that has an x in it in the question. Once I've kind of covered everything, I'm ready to substitute in. So we're going to try to substitute. It's called U-Sub because we use the letter U and we substitute. Not a very clever name. All right, instead of the quantity x squared plus 1 squared, I'm going to write u squared. Instead of 2x dx, I'm going to write du. All right, generally at this point in the question, I like to ask myself, does this look better? So if I'm thinking of things I would like to integrate, do you guys agree that u squared du looks better than x squared plus 1 quantity squared times 2x dx? I think it looks better. All right, so we're going to pretend we're just doing this question. How would you integrate u squared? All right, need to divide by 3. I like using a 1/3. Does anything happen to the du? Does anything happen to the dx normally? Yeah, it kind of disappears with our integral notation, but what does appear? Plus c. All right, we have one and only one more step. Perfect. Our question was asked in x, so we need to return an answer in x. So I'm going to keep the 1/3, but instead of u, I will plug back in x squared plus 1 quantity cubed plus c. And I'm done. What do you mean the normal way? A normal, if you wanted to solve this with methods that you knew before, what you would have to do is probably square this out. So x squared plus 1 times x squared plus 1, then distribute in the 2x and then integrate. It would be a lot of happenings. So this is definitely going to get us places that we could not integrate before. Yes, ma'am. Pretty much. Yeah. All right. So let's talk about some things about this problem. How many times do you think this is going to perfectly match exactly what's chilling in our question? Barely ever is the answer to that. So that's being very hopeful. So what we're going to practice kind of the rest of the class is how do we deal with the fact that it might not be 2x dx sitting there. It might be just x dx sitting there. It might be 17x dx sitting there. Now, not all of those what ifs will be answered because some of them are not things we can do with U-substitution, but we're going to get progressively a little bit harder. So let's go here. Actually, let's go here. Let's go to the bottom one. Because this is almost the exact same question, right? What? No, so we actually can't distribute the x because of the squared.
So we could square it out and distribute it, but we're going to try to use U-sub instead. So let's try to do this same question. It's almost exactly the same. What's just missing from this question? All right. The 2 is definitely missing. The x is kind of just in a different place. So let's try this question. I do not need help. I cannot distribute it because of the squared. I would have to like square everything first. So do you guys see a function inside another function? All right, I still see x squared plus 1. So that's still my u. All right. I'm going to find du, which is the derivative of u. We just did it. 2x dx. Now, I have to kind of play a matching game here. I find du from taking the derivative of u, but I notice that not all of that du is in my question. So I want to match what's in my question. I just have x and dx. All right, I can't multiply the original one by 2 because that's just the original question. What I could do is divide both sides here by 2 or multiply by 1/2. So I get x dx is 1/2 du. So when I go to substitute in, I'll do 1/2 du for x dx. So let's do our substitution. This will probably answer some questions. All right, instead of the yellow stuff, so instead of x squared plus 1 quantity squared, I'm going to write u squared. Instead of writing x and dx, the thing that x dx is equivalent to is 1/2 du. So here, we're kind of playing a matching game. We want to match the other stuff that's in our question. What? Being able to match it? Most of the time. Mm-hmm. All right. Now, some of you, as you're getting better at U-substitution, right now I'm kind of plugging in everything exactly where it would go. So like here, this is exactly where my dx, or my dx was. This is exactly where my u squared was. One thing I like to do as I'm kind of getting better at U-substitution is I'm going to start putting these 1/2s and things out in front of my integral to get them out of the way. That is legal with our integral properties, and it does make integrating slightly easier as we move forward. All right, so I'm going to keep the 1/2 out here for a second. We just integrated u squared. What is the integral of u squared? 1/3 u cubed, so raise the power by 1, and I'm going to add c. 2 steps to finish my problem. I'm going to choose to multiply these 2 fractions together. What would I get if I multiplied those together? 1/6 and plug in u. X squared plus 1 was still my u cubed plus c. All right, so let's try a couple more and then we'll take a break so that you can see. All right, let's do the cosine one up here. All right, this one's a tricky one. This one's mostly tricky to remember to use U-substitution. Do you guys see a function inside another function? Do you guys agree that 5x, if parentheses will help, you can put them in, 5x is inside cosine of whatever? Right, so if this was just cosine of x, I would not need U-substitution. The fact that we have something other than just x, just like that made us use chain rule, is making us use U-sub. So u equals 5x. All right, in a second, I'm going to ask you guys, so ponder, what is du, the derivative of u? Is anyone ready? What's du, the derivative of u? 5 dx. Good. So we're going to keep that there. All right. Do we have this in our integral? Do we have all of the 5 and the dx? Yeah. So my question is, do we need to divide by 5? Or do we have all of 5 dx in our integral? We have all of it. That's a good question. So we do still have the cosine there, but let's look at what happens when we substitute. So instead of 5 dx, I'm going to have the du that does need to go at the end of my integral. What's cosine of 5x going to look like? Cosine of u. All right, so cosine is going to end up being the function that I'm going to integrate. So I need to cover everything that has an x in it, but I can leave anything like cosine, sine. Those might be the functions that I'm going to integrate. So that's functioning a lot like our squared was before of the thing that I'm going to integrate. All right, what is the integral of cosine? It's positive sine. All right, and I'm done, right? I'm good to go. I'm acting. All right, uno más. All right, does it need U-Sub? All right, Sadie and Chris both said yes, very convincingly. Why? Why does it need U-Sub? All right, we got some stuff inside a square root. So what do you guys think U is? Beautiful. All right, which would make du what? All right, so du, the derivative of u is 2 dx. All right, do you guys agree with Herbie that I don't have the 2 that I need in that integral? All right, so how do I make it so that I'm just matching the dx that's left? All right, you could divide by 2. So I'm going to do 1/2 du. So when I substitute in, I just have the dx, so I'm going to plug in 1/2 du. All right. So I didn't have this 2 anywhere in my integral. It might be here, might be here. I didn't have the 2 to substitute for, so I'm going to just isolate the thing I can substitute for, which is that dx right there. So I wanted to get that by itself. So kind of this step in here is me trying to match what's left in my integral. So since I only have the dx left over, I'm just trying to match just the dx here. Matt, did you have a question? Okay. All right, so what is this going to look like when I substitute? Square root of u times what? A little bit more? 1/2 du. All right, I'm going to pull the 1/2 out to the front and leave the du at the end. Yeah, I like turning this into a power. The only thing I have is a power rule. So what power can I turn it into? Cool. All right, I haven't been asking this question, but does this look better than it did before? I would argue yes, at least a little bit. All right, so let's keep the 1/2 for a second. And let's integrate u to the 1/2. What are we thinking? What's that going to look like? 3/2 power, 2/3 in front. All right. Got my plus c. All right, I need to plug the u back in. So I'll have, what was u? 2x minus 1 to the 3/2. I would like to simplify the front fractions. Thoughts on what's going to go out front? I'm going to do 1/3 from canceling these 2's right here. Now, before we take our break, I just want to ask one question. How could we check our answer? We just found an antiderivative. I could take a derivative, right? So let's say I take a derivative. I keep the 1/3. I bring down the 3/2 power, 2x minus 1 to the 1/2 power, and then this would chain rule. So I'd have times 2. If you look at what would cancel, the 3's would cancel, the 2's would cancel, and I'm left with the square root of 2x minus 1.
Whoa.
So kind of a powerful thing as we start thinking towards our end of year tests, think about your multiple choice on your AP test. If you're finding an antiderivative or you're finding a derivative, you could do the other one to kind of match with multiple choice answers, which is pretty exciting. So there we go. All right, when we come back from break, we're going to try just a couple more that are like this, where the constant doesn't match, that look a little bit weirder. Then we're going to add in a different type of integration with e's that we did before and bases that are not e. If you're wondering what happens if the du doesn't match and there's like an extra letter somewhere, we're going to answer that the next class we do notes. If you're wondering some other what ifs, they might be answered either later next year or possibly never. So let's take 5. Have fun. Oh, goodness gracious. So many emails. I can email you a PDF if you need it, or there's extra copies in this binder right here if you need one. Thank you. This blue one up here, This blue binder. Yes. Mm-hmm. Mm-hmm. All right. Let's try these last few problems just real quick, and then we got a notes check. And if we end early, we end early. It'll probably happen. All right. Thoughts on this one? We got another cosine. We got some stuff. Does it need U-sub?
Yes.
Yes. We see stuff inside another function. So what do you think U should be? What are your thoughts, everyone? X to the fourth plus 2? All right, I like that because that is inside the cosine. So we've got this guy inside the cosine. Again, we don't need kind of coverage for that cosine. That's going to be the function we end up integrating. I am concerned about this x cubed dx. So let's take a second and pause to find du, the derivative of u. 4x cubed. Now, one thing a lot of students, and I'm going to add the dx at the end, a lot of students get confused about is the fact that this process right here has nothing to do with the actual integral itself. We're just taking the derivative of u inside the problem and then comparing back up. All right, let's look and see if we've got what matches. So here I have x cubed dx in my integral. I don't have 4x cubed. So do you guys like Herpes' idea of trying to divide by 4 on both sides of this equation? I do as well. Y'all, this is one of my favorite topics, and you seem very sad about it. I always hate when I teach something I like and no one takes my sales pitch and they're like, I mean, I do. It is the same thing. It's just we're widening our scope of the integrals that we can do. It's very exciting. Oh yeah. Yeah, but like it doesn't always make it quite as wide. I don't know. I really like algebra, so anything that's like very algebra based is like I do. I teach algebra 1. Natello teaches that? No, I think BC is my favorite class, but that's because I like their content. I get to use harder questions too. A little more interesting. All right, what's this going to look like when I substitute in? Five. All right, cosine of u, going for the cosine of the x to the fourth plus 2, times 1/4 du. All right, if you're starting to feel comfortable with your u-sub, I am always going to check this constant out front just to get it out of my way. The only thing that has to be in the right place is this du has to be at the end. Remember, we're using that as like a closed parenthesis for our integral, so that has to go at the end. All right, the 1/4 is going to stay. Thoughts on the integral of cosine u? One thing that does make u-sub difficult as well, especially with sines and cosines, is this is the first method we've had where we're doing derivatives and integrals in the same question. So you do have to be very careful, especially with sines and cosines with those negative signs. It's a little difficult. This good, this done? No, Herbie's telling me I got to plug you back in again. All right. So x to the fourth plus 2. Now, you may be noticing having this written down at the beginning, the u equals and the du, all of that's really helpful and necessary for kind of us to figure out where we're plugging things back in and what we're doing. All right, let's try this last one. Does this one look any creepier to anyone? I think so too. Do you think it needs u-sub? Why? All right, we've got x squared plus 1 is inside the power of the 20 on the bottom. I keep asking you that because eventually I'm not going to tell you that you need u-sub. You're going to have to figure that out yourself. So we're going to keep looking for those reasons why we're using this method. So we've got x squared plus 1. All right, thoughts on du, the derivative of u? 2x, is that it? Dx. All right, let's look for coverage. Oh, this is interesting. Yeah, I like that idea. So we have a 20x dx inside our integral, and we have a 2x dx here. You have a couple of options. I could divide by 2 and just substitute in for x dx and just kind of leave the 20 hanging out. Or we can try to match that guy by multiplying by 10 on both sides. So 10 du is 20x dx. All right. So when I substitute, I'm going to substitute 10 du for this 20x dx. All right, let's substitute and see what that's going to look like. All right, so I'm going to go ahead and put my 10 du on the top and my u to the 20th on the bottom. That looks a little creepy, though. Ooh, yes. Derek had a great way to make it less creepy. Derek, what'd you say what you said again? U to the negative 20. That'd be a great idea because I don't have a quotient rule. I can't integrate things when I have them in the denominator of a fraction. So bringing that up as u to the negative 20th would be a great idea. All right, let's see if we remember our integral rules. I'm just going to keep this 10 here. Ooh, pointy 10. What will the new power be on u? Negative 19. Way to go, Matt, for adding 1. You guys haven't had as much trouble as my students normally do with negative numbers and adding 1. All right, I'm going to add c at the end. And I can already hear Herbie yelling at me to plug my u back in. My u, I can scroll back up and see is x squared plus 1. And I'm done. All right. The last thing we're going to talk about today, which is going to be super easy to do, is, yeah, there's going to be a really helpful hint, is exponentials. Does anyone remember what the derivative of e to the x was? So what do you think the integral of e to the x is? Almost. Plus c. All right. This guy right here, does anyone remember the derivative of a to the x? All right, this one was allowed to be blurry. So this one had an a to the x in it, but we multiplied by something because the base was wrong. What we multiplied was natural log of that base. So for example, 2 to the x, the derivative would be natural log of 2 times 2 to the x. If we multiply by that natural log of a to take the derivative, what do you think we'll do to find the antiderivative? Divide it. So this will be 1 over natural log of a times a to the x, again, plus c. If you're talking about these two rules, e to the x needs to be super duper clear in your brain. That one's allowed to be pretty darn fuzzy. That one's like, I want to get a 5 on the AP test. Let me make sure I know this. Or let me study it right before the Unit 7 test. All right, now when we're looking for inside functions and we're doing U-substitution, a general helpful hint is to set u equal to our exponent. Just like exponent, sorry, I can't spell and talk at the same time. So just like with our trig functions where cosine x is turned into cosine of something else, e to the x is usually going to turn into e to the something else. And that something else is going to be what we want to set equal to u. So let's roll through these really quick and see if we can figure them out. All right. Do you think it needs u-sub? Yeah. How do I know? That exponent isn't just x. What do you think I'll set equal to u? All right. And just cosine. We just want that exponent as our u. Nope, because that's going to end up being like the cosine. That's going to be the thing that we integrate. All right. What is du, the derivative of u? Good. I like that you guys remembered that the derivative has the negative for the sign. Do I have this negative in my integral currently? I can divide by a -1 to move it over as negative du is sine x dx. All right, using my little color coding. This is going in for sine x dx. This is going in for u. Notice I don't have coverage for that e. That e is going to function as my function to integrate. Not minus du. That negative sign is like a negative one that I'm multiplying by. So honestly, what I would do with that negative sign, let's just pull them out front. All right, so there's your u and your negative du. All right, I'm going to keep the negative. What is the integral of e to the u? E to the u. Don't think too hard. We're going to add c. And then hopefully you can hear Herbie in your brain. Plug that u back in. Yeah, I like the ones with e. They're easy. Wow, bad jokes today. Trying. Does this need U-sub? Why? All right. You said negative 5x squared, Matt. You think that's our u? Perfect. Thoughts on du, the derivative of u? Negative 10x dx. All right. That does not match what's in our integral. All right. That's one option. Why is Matt saying divide by negative 2? All right, that could make the positive 5x dx in there. Another option would be to just leave the 5 where it is and just solve for x dx. Either one is fine. What do you guys like? Do you guys like Matt's idea? All right, so just divide by negative 2. All right, cool. I'd probably do it this way. As long as it's a nice number, I'd probably make what I see in the integral. The only time I would do it the other way is, let's say that 5 were instead of 7. I probably wouldn't try to make a 7. I'd probably just leave the 7 and then try to solve for x dx.
And then you just add the 7.
So if that were a 7, I would just let it kind of hang out there. So here, I'll show you what I'm, oh, that is not. So if that had been a 7, I would take my du is negative 10x dx, and I would just divide by negative 10. So you'd have negative 1/10 du. Yes, exactly. So whatever number is there would just be multiplied by whatever constant I have. So it does match the negative 1/2 because 5 times the negative 1/10 is my negative 1/2. So either way is fine. It is sometimes cleaner to do it the way Matt's suggesting if we can find the easy way to make that number.
Will we ever have to do that?
Which one? The top one? So let me substitute in that way just so you can see what I'm doing. So here, if I'm substituting the way I did, I would take this and just substitute it, for x dx. And I would substitute my u for this. Notice I didn't highlight the 5. That's okay. It doesn't have any x's in it. So it would just hang out in my integral as the 5. The e to the negative 5x squared would be e to the u. And then I'd have negative 1/10 du for the stuff I highlighted in blue, that dx, the x dx. Cool so far?
I don't understand
Why I would do that? Yeah, so let's say, Satya, instead of being a 5, this were like a 7. I can't think of a really clean way to get a 7 here. So what I could do is if this had been 7, I can make the fraction, I can just multiply these two numbers together to get the fraction, even if it's not like a super nice one. Yeah, so I can substitute for whatever part I want. So I could just substitute for the x and the dx instead of matching the number as well. So I could just keep the constant there and just match for the x dx and then multiply whatever constants I have together. Exactly. Now, if you do it like Matt, notice that we're going to end up in the same spot. is I'm going to take this 5 and this -1/10 and multiply them together. I'm going to get the exact same -1/2 that Matt would have substituted in at the beginning. So either way is completely fine. We may practice some more next time where the numbers won't match kind of as cleanly as this one is. So we can practice with that as well. All right, let's integrate. What's the integral of e to the u? E to the u. Are you guys comfortable if I integrate and plug my u back in at the same time? All right, so e to the -5x² plus c. All right, dos más, and then you don't have to listen to me anymore. Yeah.
What's the point of like? Oh no.
All right, is this one scary to anyone? All right, you're gonna trust yourself. All right. So U-sub can take care of integrals that do look quite a bit creepier than they have before. So what are your thoughts on what u should be? All right, so 1/x, I like that idea. Now, we don't normally take derivatives of things that look like that. So is there a way I could rewrite 1/x? X to the -1. This is a good example of a question, and these are going to start to come up more and more as the year goes on, of questions that I might not see the exact ending to the question as I start the question. I might just have to start with the tools I know and hope for the best that it's going to work out. So let's take du, the derivative of u, and see what's going to happen here. What are your thoughts on the derivative of x with a dx, right? All right, Herbie sees it. Does anyone else see it? Oh my goodness. Wow, that's cool. All right, if I put the x back on the bottom of this fraction, I'd have x to x squared. Or if I think about moving this guy up, we have x squared, x to the -2 in our numerator. All right, hold on with that. If it helps you to write this like this guy, this helps my BC students a lot to see what's going on. That is a legal way to rewrite because I would multiply that e to the 1/x up to the top in the numerator. All right, let's look at what we have coverage for, what we might need to rewrite. U is here. That's great. Now, does the du match exactly? So our du in our derivative part is negative, but we don't want it to be negative. So I'm going to do this. Effectively dividing by -1. So this guy is going to go in for this. All right. What's this going to look like when I substitute? What's e to the 1/x going to look like? All right. What's equivalent to 1/x² dx? Negative du. You can put it on the outside. You want to make sure it doesn't look like you're subtracting. All right. Keeping the negative, what's the integral of e to the u? Don't think too hard. All right. We're going to just do e to the u plus c. And then I'm going to plug my u back in. I'm going to use the 1/x. You could certainly use the x to the -1. See how brilliant you are now? It's a lot of learning we've done. All right, last one. Definitely not best one, but A1. We do, because this is so much better when you practice. Yep, so those checks are really good for you guys.
They should put in other classes.
Do you not do something at the end of your class?
No, not really.
How do you learn things then?
No.
Oh. So as much as you complain about notes checks, you realize that they're valuable? Is that just my BC class then? They complain a lot.
Yeah, we play.
How would I make problem sets better then?
There's no way. Yeah. The only way is just make them slightly short. That's it.
What?
They're meant for practice.
Yeah.
Like if these-
I need to build in more time for problem sets in class. Less trig questions.
It's either that's true.
There are far less trig questions this year than I normally ask, to be fair. Yeah. Not a lot, but yeah.
Like by like 30.
Like normally on the next class's test, I would ask you to integrate something and plug in bounds that are like pi over 4 and pi over 2. All right, last one. Does it need U-sub? Why? Because of the 3x. Cool. If you need help figuring out if it needs U-sub, Matt's apparently doing a really good job of this. So what is U? Well, keep doing that because they're good guesses. All right, U equals 3x. And we're trying to get an intuition for this because we kind of have to figure out what do these questions look like versus what do other questions look like. All right, so what is du? 3 what? Dx. Sorry, pet peeve is people leaving off that dx. Oh, not the 2/3. So I understand why you're saying that though. So what we're going to end up doing here, this base is not something we want to match. That's going to act a lot like our E is. So we don't need to cover for that. We just need to divide by 3 so we can match just the dx. So we're going to do 1/3 du is dx. Hold. Kirby, you go so fast. Can't keep up. All right. So that 2, that base is going to stay. Just like the E did in our other question. So our 2 is going to stay. What will its new power be? U. All right. And now I have 1/3 du that I need to plug in for the dx. Yes, this is the substitution step. Now, if you're starting to get comfortable with substituting, one thing I like to do a heck of a lot is put my 1/3 out here and my du at the end. You'll see me do that a lot as we keep progressing because those fractions are usually easier to put out at the beginning. The only thing that does need to be in the right place, that du has to be at the end because that closes out our integral. Now, this is one of the rules we have up above. We are going to have 2 to the u as part of our integral, but what are we going to do to correct for the fact that we have 2 as our base and not e? 1 over natural log of 2. All right, so that's only coming up. It's this guy right here, this rule right here. You're not going to see it very often. If you're talking on the AP test, it's like maybe 1 multiple choice question out of the whole test. I'll probably ask you 1. Yeah, so essentially there's not, the way to actually prove it is with the change of base formula. They don't teach in pre-cal anymore, I'm pretty sure. But essentially we need to correct for the fact that the base is not E. So if your base is anything other than E, for derivatives, you're going to multiply by natural log of that base. For integrals, you're going to divide by natural log of that base. Because all of our bases were E. So if we did that,
No, not like the full.
none of those were of the form like number to a power. We were talking like x to our powers. Cool. Love the what if questions. Perfect. Is my answer done? Ready to go?
Yeah.
Why not? Got to plug back in for you. I'm going to personally combine these fractions into 3 natural log of 2 on the bottom, just multiplying those 1s on the top, 2 things on the bottom, and I'll have 2 to the 3x plus c. We're done with notes for today. I am going to give you a notes check mostly because this stuff is so much better the more you practice, because there's a lot of decisions you have to make. You have to make a decision, do I even need U-sub? You have to make a decision, what's U? How do I solve for the du? So we're going to practice that before we leave. I will say we have about 11 minutes. There's 3 questions. I bet you can do it.
If we don't use it, but we just do it, there say don't. Like if it says do it using U-sub and you're not.
So I'm probably never going to tell you to do it using U-sub. You're just going to have to.
This isn't going to be on the test on Thursday.
This is not going to be on the test on Thursday.
The only way this could be on the test, if you choose it to be on Thursday, is let's say I gave you something. Here's ooh, that was loud. This would be a really good example. Let's say I gave you something like this. One way is you could use U-sub, but you could also multiply out 2x plus 1 times 2x plus 1 and just multiply, like foil it out. You could do that, or you could do U-Sub. So if you,
Like, that's gonna be on the test.
it could be.
Like, you could, you'd like, something
So you could do it with U-Sub if you wanted to. That's a mathematically legal way to do it. Multiplying out, also very mathematically legal. When we get to ones where I'm going to force you to use U-Sub, you can bet that this power is going to be something like 6, where you would not want to multiply that out. You could, it would just take a half of a one. Pretty sure one of my BC students did something like that to avoid U-Sub, and it turned into a gosh darn nightmare. Yeah. It was humongous.
Well, this was technical.
Why? Because I made the font big. Sometimes Word makes the font so small. All right, so I'll tell you all 3 of these definitely need U-Sub. Possible to do it without? I mean, yeah, if you want to take something to the 8th power or 5th power or whatever. Yeah, that's a lot. 7th power. Good. Yeah, the next time we do notes, we're going to just do more U-Sub. We're going to bring back what does natural log look like. Might even integrate into some arctangent just to make everyone real happy. Don't like arctangent? It does cool stuff though. What other graph do you need to give them her? We're walking through the good. There's a 3 blue ones out. Maybe I'll go with you. So one of my other ones, maybe the 5 acres. One of my favorite ones. All right. If by the end of class, if you're feeling good about this and want to get up and find someone else who did the same version as you, or I think I can do these in my head. So, yeah. That would be outside of the. So you're going to get one set of crafted up with. I guess like could happen if I did like something that was a trig derivative, so like secant something, tangent something, that is a derivative of the secant. So I could do it that way. That'd be a little harder.